So, hi students, you're welcome once again to another video of mine. And today is our mostly academic physics channel, and we are going to be considering our hydrostatics, another important chapter in our syllabus of physics. I am going to divide the video into two sections, and as usual, this lesson is going to discuss mainly about an introduction, and we have some couples of questions and illustrations which we are going to solve with respect to that. Like I said, you need to do more practice on your own so that you can get that confidence and you know how to actually tackle questions when they come your way. I'll cover all what is required with respect to our syllabus, and I'll make sure I break it down into the simplest possible way that everybody should be able to understand. I believe you'll be able to understand. So we start by definition of pressure. And I know by what I believe from early classes, we might have studied that we define pressure as the force acting normally or perpendicularly per unit area. So we can say pressure is just force acting perpendicularly per unit area. So that is the definition we give to force. And I said force to pressure, and we can write that mathematically as a pressure is the force acting normal. Normal is simple as perpendicular divided by area. So the SI units of pressure are numerous, but you need to keep it in mind that force is measured in Newton and area we measure in meters squared. You combine these two together, you write it as Newton per meter squared, both screw, or Nm raised to the power -2. So these two is correct, and this is the definition we give to pressure, or we give to pressure in physics in basic class. So similarly, we also need to understand that when we talk about pressure in fluids, because one thing we need to understand about this pressure, which I believe we might have learned in early classes, that pressure do act in solids, liquids, and gases. In fact, in early classes, you might have been told that the a body will exert the greatest pressure when it is standing at the tip of its toe. And the reason about that for that is because the tip of the toe contains a very, very small area. So numerically, from what I have written here, you can relate and say pressure is inversely proportional to area. And because pressure is inversely proportional to area, it simply means at low value of area, the pressure will be large. So we keep that at the back of the mind that the relation between pressure and area is such that the higher the pressure, the lower the area, and vice versa. So this is the way we relate that. But now we want to consider pressure that acts in fluids, and that is why we call it hydrostatic, or you say static fluid or static pressure. Now, looking at what we have here, we have a bucket or a beaker, if you like, that is filled to the brim and is having an height of h and an area of a. Now, what we say about pressure, I want to talk about liquid pressure or fluid pressure generally. So considering fluid pressure, we can say the pressure acting at any layer of this fluid. You can see water is flowing or the liquid is flowing horizontally. And because they are flowing horizontally, you can say the pressure acting at any layer of this fluid, at any point of the fluid, we can take any desired point. Now, but here we want to consider the pressure that is acting at the what? At the bottom of this container for the first what? First consideration. So if we take the pressure at the bottom of this container, let's say at this place now, I'm calling this one at point P here, which is the bottom of the container. I want to go, okay, let me use another alphabet, point B, which is quite okay because P is pressure. I don't want us to have issues. So we can say the pressure at point B. Let's put that in writing. Pressure at B So we say pressure at B is due to the whole weight of the container. We might have learned from early classes that the weight of the body will always act downward. So the whole weight of this container, which we call the weight of the container, as we've talked about here, which is same as the force, divided by the area, which is that. So weight is force. You might have also studied that. So now here, we also know, as a matter of fact, from early class, that weight of a body is equals to the mass and its acceleration due to gravity. So substituting that, we can say the pressure at this point, I write that pressure at B is equals to the weights. Now I'm substituting M and G divided by area, which is more or less like what we have here. But we can now continue to break this thing down in the sense that we also might have studied in early classes that the density of a liquid or density of a substance generally is always equals to the mass of that liquid divided by the volume. So generally we can say, let's quickly recall. We might recall that density we denote by rho of the liquid is equals to the mass by the volume, which we denote by V. So now on, I will be taking my mass to be M and my V and my volume to be V. So directly I can substitute here. I can say mass is what I have here. So I can say mass is equals to the density, which is rho, times the volume, which is V. So directly I can say that pressure at B acting through the whole weight of the container will now be equals to mass, which I will substitute rho, and you have Vg divided by the area. And also recall, let us quickly recall that the area of the container, recall also that area is equals to, I need to always keep this at the back of our mind, the area is always equals to the area is like saying length times breadth. In this situation, looking at what we have here, the length and breadth here is, we are talking about, look at this now. You have to be careful. You can say height and this. Please, you can always keep that at the back of your mind. So area can be equals to, we can say height times the distance from here to here, which you can call the length. So anyhow you want to do that, always keep it at the back of your mind that the length can be taken in terms of that. Another thing is you can say, let me do it in this way for quick understanding. Let's do it in terms of volume for understanding. Now, the volume of a substance, is equals to the area of that substance multiplied by the height, which is what is given with respect to what I have. So area A multiplied by the height H is going to give me the volume. So if we substitute that directly here, my dear student, we say this is over A. So directly we can say finally that the pressure at B is nothing but equals to, we have rho, which is density. Please, rho is not P. P is pressure, rho is density. Density acting on the fluid. Density is mass per unit volume. The volume is the space occupied by the container. Please keep that at the back of your mind. So we say rho multiplied by volume, which we have just discovered that is area times H, A times H, multiplied by G. We are dividing everything by the A. From what you have studied in early classes, A gets cancelled out. And if you look at that directly, we can conclude that the pressure, which we call the gauge pressure at B, is nothing but what we call rho Hg, or basically most of us know it as H rho G. Anyhow you want to write it, which is the same thing as your H rho G, is also valid. So keep that at the back of your mind, as pressure due to the whole weight of the container is given by the formula of H rho G, which is quite important for us. And this is also called the gauge pressure. Please keep that in mind. It's also called gauge, or you say gauge pressure. So that is that about that. And that is the introduction with respect to this formula, which we need to keep at the back of our mind to solve a lot of numericals, and that is not all. Now let us quickly consider another situation, which I'll also do by this side. For us to understand this very well, let us quickly look at another form or another situation with respect to the diagram we have here. Now, looking at this diagram very well, you can see if the top of the container is open like this, there is another form of pressure we call atmospheric pressure, which basically in early classes is defined as the pressure that is exerted from the atmosphere. So if it is open and an atmospheric pressure is coming in here, we can now say that the pressure at the top of this container is pressure here is nothing but P atmospheric, which I'm writing as PATM. You can write it, some of you are used to writing it as capital letter A. It's still the same thing. So what we're now saying that the total pressure that we now add throughout the bulk of this container is nothing but, we say total pressure now, will now be, you can say total pressure I call PT, will now be the atmospheric pressure I call P atmospheric, plus the gauge pressure we have just, which is rho hg, or you say h rho g, which is you are familiar to. And this also is very important when atmospheric pressure is acting on top of any liquid. We always say the amount of pressure or the absolute pressure, the total pressure acting on top of the container throughout the container will be the sum total of P atmospheric plus H rho g, which some of you always love to write as total pressure at this container at the top throughout the container will now be atmospheric pressure. Most of you are used to this, A plus H rho g. Both of them are valid, and please, you can always keep that at the back of your mind. So guys, we move quickly to the next slide to discuss the next one, which I believe we are following. Let's move on to the next slide. Now, about the next slide, we have, oh, wow, very good. Now, about the next slide, we have a manometer, which is an open tube manometer. Now, this is another thing which is very important for us to keep at the back of your mind, because we are going to face questions and numerical, either O-level or advanced level. We have to understand some concepts of how the manometer works. Now, basically, in early classes, we might have been told that the manometer, you can write this, manometer is used to measure fluid or liquid pressure, which is also very valid because of some questions that are non-numerical. So when we say liquid pressure, that means solid pressure, we have another instrument we use to measure that, which I believe you might also have studied in early classes. We call that Barrow Barometer. In fact, there are different types of barometer, which I'm not going to be talking about. And the popular one you call aneroid barometer. So be that as it may, we can also say manometer can also be used for measuring the pressure gauge in a particular chamber. As you can see, this is a chamber. I'm trying to move away from here so that you can actually see the picture very well. And let's do that very quickly for us to get what I'm talking about. Now, as you can see here, we have we said it can also be used for measuring. Let's put that down. Measuring pressure gauge in a chamber. Now, how does it work? Let us quickly talk about how it works and look into one or two things we can talk about in this stuff. Now, we can see this is filled with gas. Now, please, you can consider this. There's a gas here, and the gas is exerting a pressure which has a particular liquid. You can see the liquid here is different from the liquid here. Diagram not drawn way here, but we have to just explain the principle so that we can all get it. Now, what we are trying to say here is that there is what? There is a liquid. We have different liquid at this point. Now, let's say the pressure of this gas, I will take it at our pressure of this gas, I will take PG. Let me just say pressure of the gas is PG, pressure of gas. Now, this is the liquid that is filled here. This place should be open, please. There should be an open because of atmospheric pressure. I'm still coming back. Now, when you look at this closely, it is the pressure of this gas that has pushed this other liquid. You can see this is another liquid here. So let us now consider an horizontal line, which is what I think the artist that is trying to draw this try to draw out for us, but not drawn well. Now, any line, any horizontal line that is taken between the layer of liquid will always have the same pressure. I think in chapter 2, or maybe it's part of this chapter, I don't know, because from the way this slide was prepared, we are going to talk extensively on Pascal's principle. I have some video online on my YouTube free channel. You can check on Pascal's principle, which I did on board. Or I can also take it again in this because it's also part of the of the syllabus, which you need to break that in such a way that all students we understand. So back to what I'm trying to say, my dear students. My point here is that within any part of liquid, when you draw an horizontal line, the pressure is always the same. But you also need to be careful. At this particular point, this is the height we are considering. We are considering the height from this particular height. The diagram is not drawn to scale, but we explain it in such a way that everybody will get it. You can see, let's say the pressure at this particular point, I'm taking it as a, we say pressure at any point here will always be the same. So I'm taking here as point X, which is also point X here too. So what I'm trying to say is that the pressure at any point of this horizontal line will always be the same. Why? The reason is because we have actually said pressure does not depend on the shape of the container. I am still coming to that, which I will still talk about. Why? It does not depend on the shape. It only depends on the height. Now you can see this is the height. According to this diagram, that is the height. So any line that is drawn horizontally, no matter how the shape looks like, the pressure acting on that particular line, in that particular horizontal line, is always going to be the same. Now, let us not make mistake, because there are two different liquids here. The first one is liquid. You can see this is liquid one, and this is liquid. If I should draw that line here, and these are both these, where I have two different liquids, the pressure acting on each of them is not the same. I hope we understand this so that we don't make mistake. Now, from what we have studied that because this is open, there will be a pressure coming from here, which we call P atmospheric, which most of you love to call atmospheric pressure. You denote by it. So we can now say the pressure acting throughout this thing. We can say the total pressure that will be exerted by this gas, or pressure at this point X. For example, I can say pressure at this point X, pressure at X is equals to the atmospheric pressure, which is P atmospheric, plus the pressure inside the liquid, which is always H rho G. We've talked about that. The liquid exerts a pressure, which is H rho G. Then the atmosphere also has its pressure. The total pressure at this particular point, as we are coming like this, with the pressure of the liquid plus the atmospheric pressure. Now, similarly, the gas was released. As the gas was released here, you need to keep it at the back of your mind that there are different things you can always consider. The pressure of this gas that is coming here is the same thing as the pressure of at X here, because this is the way it is coming. You can see, and it comes here. So we can say the pressure at X is the same thing as the pressure of the gas. So I can say the pressure of the gas minus H rho G is the same thing as atmospheric pressure. So this is the formula we use, and this is the formula you need to keep in mind whenever you are trying to solve questions on manometer. It is very, very simple to understand the concept of manometer, and this is the way we do it. Or you say Another way you can always keep it back of it, which I think is better, you can say the pressure of the gas minus the atmospheric pressure, that is P atmospheric, is equals to H rho G. So this is very important, and this is what I want you to always about. So when you have numericals that ask about how to solve manometer, keep it at the back of your mind that at any horizontal line within the layers of the liquid, the pressure is always the same. And if you have two different liquids, you draw an horizontal line, pressure is not the same. So this is what we have studied, and this is just the introductory part of the what? Of the long concept we still want to learn, which we all need to follow one by one. So to understand this very well, we are going to be considering some illustration, which is going to help us to understand all this that we have studied so far very well. Again, we can quickly just take a good example. If I should say the height of this thing from here to here is 10 centimeter, and I say the height from here to here is 3 centimeter, you can always use this direct formula. I will do a lot of illustration to break down all this stuff. I'm trying to make it very slow, steady, but also straight to the point. I believe you can hear me, and I believe you guys are following. Now, by virtue of what we have studied, let us take some example on all this stuff, and let's see how we understand the concept. So now we say we can do that in the next slide. We have some illustration which we are going to tackle here. Let's quickly look at them and call it a day in the first part, which is the introductory part to hydrostatic. Let's check the third one. Yes, now we have the third part, and about the third part, we have questions on. It says, what is the height of a liquid column in a barometer? In a barometer tube that would support an atmospheric pressure of 102,000 Newton per meter square if the density of the liquid is 2,600 kilogram per meter cube. So directly, we can quickly do this. And if we want to do that directly, I think there are some parameter that is needed to be given, but I believe we should know it. We know that now there's an atmospheric pressure. The total pressure of that will be PT, will be equals to P atmospheric plus H rho G, which we have studied. So now directly we can just put the value from what we have studied. Now we need to understand one thing. We are looking for the height of the liquid when the atmospheric pressure is given to be equals to, we have atmospheric pressure, which is P atmospheric, is given to be this. In fact, this should be Newton per meter square, fine, and the density is this. So we can just do that. We need to know the height of this liquid that brings about the atmospheric pressure of that. So from what we have studied, we can say the pressure, in brackets, there should be a constant. This is an incomplete question. The total pressure of this should be given, and G also should be given. We know G from what we have studied. This should be 10 meters per second square. And atmospheric, the total pressure acting on this, I don't know. So that is why this question is invalid. And I cannot be given value. I think there's a typo. I am not sure about the person that actually write out this. This is a typo because the total pressure of the whole liquid column will be given so that we'll be able to calculate the height of the liquid. So that is that about that. And that is what I think we need to do. So we just need to understand that. And maybe we go to the second one. And I think that one should be a very, very valid question. I don't know the value, and I'm not sure I have the material that this was carved out. It was Uni 9090 question 13. And I am not sure I have the question here. Uni, I don't know the uni. Maybe it's Unilag question or UTMA. I'm not always the one that compile the questions and the illustration. They're always been done by one of our students. So the next question, I just believe this is an error, and if not, then the question cannot be solved because you don't know the total pressure. So the second one says, a well 1 km deep is filled with a liquid of density of 950 kilogram per meter cube. If the atmospheric pressure is this, the pressure at the bottom of the container is dash. So this is what we need to understand, that this is also the pressure at the bottom of the container. So atmospheric pressure, we've studied that the pressure, total pressure, is equals to atmospheric pressure plus H rho G. From what we've studied, we can actually put the numerical values here. Here we are given the atmospheric pressure, which is given as say this is 1 times 10 raised to the power 5, is 10 raised to the power 5. We are adding the value to the height. The height is 1 kilometer, which we know is simply as 1,000, we write as 10 raised to the power 3, times the density is 950, and G is always 10. So directly, I can say this is the same thing as, let's do simple mathematics, 10 raised to the power 5 plus, this should be, it's 10 raised to the power 1. Then I can write this as 10 raised to the power 3 times, this is simple as 95 times 10 raised to the power 1 times 10 raised to the power 1. Just want to bring this for understanding's sake. 10 raised to the power 5, then plus, this is 3, 4, and 5, plus 10 raised to the power 5 multiplied by 95. So we can factorize. 10 raised to the power 5 is common, because in the absence of calculator, 1 plus 95. 95 plus 1 is 96. So direct answer to this is 96 times 10 raised to the power 5. Because we are looking at the pressure at the bottom. Pressure is always measured in Newton per meter squared. So this is the answer, or you write it as 9.6 times 10 raised to the power 6. It depends on the option, and that is how to solve question of this nature. So keep that in the back of your mind, and that is how we solve this. I hope you understand this. Like I said, the first question is more or less like this question, but the only missing stuff there is just the fact that we are not given the total pressure. Or we can check it again. What is the height of the liquid in column of a barometer to that would support an atmospheric pressure of this? And if the density, I think we are the one that misinterpreted this. This should have been the atmospheric pressure is supported by the pressure. So it is the atmospheric pressure that is the total pressure acting on this and is equals to H rho G. Sorry about the English. So here we can say directly it's just substitution, which I believe every one of us can do. This is 1, 0, 2, 1, 2, 3, according to the question. It is given. We are taking the height, which is unknown. The density was given to be 2600. We are multiplying that by 10. They can cancel directly. All these we get cancelled out. 1, 2, 3. So making H subject, we have H is 102 divided by 26. And I think that should be easy for us to do. And if we do that one well, 26 times 4. So it's not up to 4. We can just punch calculator. 102 divided by 26 is giving us 3.92. I'm working in meter, and that is my answer to this one. So be careful about this. It is grammatically correct because we are told that it would support, this is the word, support the atmospheric. That means the pressure is the atmospheric pressure. Please, sometimes you need to be good in English to be able to solve questions. So we have 2 more illustrations, I guess, and let us quickly look at that before we call it a day here. The other 2 illustrations we have here are, yeah, fine. I believe we can see this. Now, the third one, which is illustration 3, is as a result of air at the top of a barometer. The height of a mercury column is 73.5. centimeter when it should be 75.0 centimeter. The volume of the space above the mercury is 8 centimeter cube. That means it displays a volume. Good. Calculate the correct barometric height when the barometer reads 74.0 centimeter and the volume of the space above the mercury is 6.0. This should be centimeter cube. So to solve that directly, illustration 3, you need to understand the way the barometer was constructed, and so that we can apply the formula of our pressure. Now, remember, we talked about pressure exerted from the atmosphere, we call P atmospheric. Now, as a result of air on the top of a barometer, diagram not drawn to scale, just permits me to just explain. There is air on top of a barometer. There is a liquid which is filled with liquid. You can see this. This is the liquid, and this is the barometer. I mean, the barometer is inverted like this. For you to get it well, that is why illustrations are very good. Like I do say, you have to practice more to be perfect. You need more practice questions, and you attempt them, and you are going to be perfect. Now, as a result of air, so that means there is air. As a result of air, on the top of this, the height of mercury column is 73.5. The height here is 73.5 centimeter, because there is air. Air, you know, air is vacuum or vacuum. And how you want to do that, always keep that at the back of your mind. So here we are told that when it should be 75. That means normally, if there is not, if we don't have any air on top of this, if it is filled normally, the height of this stuff should be 75. So that means if we have this normally here, the height of this should be 75.00 according to the question centimeter. So we are taking it gradually from understand. So that means there's an air on top, which is as a result of the way the tube was inverted. So be that as it may, we can now see the second premise. We are told here that the volume of the space above the mercury is 8 centimeter. So this vacuum has the volume we have considered, and we are told that the volume here is 8 centimeter cube. So now the question now asks us that we should calculate the correct barometric height. Calculate the correct barometric height when the barometer reads 74.0 centimeter and the volume is 6. So now what we are talking about now is that here now, there is another one, which is the one that is reading at an unknown height. That is what we're talking about. At an unknown height, the barometer is reading 74.0 centimeter. So now we are to consider, let's just draw. It is having a volume of 6.0 centimeter cube. So what we need to do is to understand the logic of our total pressure. You know, the total pressure acting when atmospheric pressure is acting is always equals to the atmospheric pressure plus the gauge pressure we call H rho G. So directly, my dear students, what we need to understand here is that when we consider our example in the concept video, we talk about pressure coming from the atmosphere. In this case, the tube is inverted. So when the tube is inverted, the total pressure will be lowered because pressure depends on height. As the height is increased, pressure tends to increase. From the formula we said, pressure is H rho G. So pressure do not depend on the shape of the container, but depend on the height of the container. I've said that in the concept video. Now, In illustration now, we can directly say, because this is inverted, that is upside down, the pressure, atmospheric pressure, minus H rho G, which we said this H rho G is the pressure gauge, which depends on that. My point is pressure always depends on height. So if you say H rho G here, because rho and G is not given, I am only considering it as the height. So I say P atmospheric minus the height. So here, the atmospheric pressure, which is the total pressure initially, was 75 because there's no space. So that is the one that is coming in. So that's what we see here was that only 73.5 was what? Red. So, and we said something the other time that whenever we have a fluid and we draw a straight line, the pressure at that particular horizontal line at any point inside that horizontal line or along the horizontal line is always the same. So you always need to keep this at the back of your mind. So if we want to consider this, what I'm trying to say is that the pressure of this particular substance at this particular line, which I call an hypothetical line, I can say the pressure at that point will now equals to the atmospheric pressure, which is 75 here. Because when there's no space, the atmospheric pressure was 75 from what I have here, minus what we have here. You can see. So we can say here, what we have here is like saying H minus H. I'm trying to subtract the pressure, atmospheric pressure from the height at which this we are having is 73.5. The reason I am subtracting is because it's an inverted tube. So we can say the pressure at this point is just 1.5 because when you subtract 75 minus 73.5, you are going to have 1.5. So here, the same thing also happens. The pressure here will also be the atmospheric pressure, which we take as H, minus the height of this, which is 74. I'm using the same formula, which is here. So you can always follow this to understand the concept. So pressure here is now equals to atmospheric pressure at this point is the height we are considering. The height we consider for this was 75, which was the initial value without any space. The height was here was 73.5. We take the subtraction, we know pressure will be the same at any point. So here also, as we come to this side, the pressure, atmospheric pressure here, which is the height of this container, which was what we are asked to look for, minus what was being read here was 74. So this is the first pressure. This is the second pressure. So be careful about all this type of question. This is the way you break it down. What I've done is just to understand, okay, because of air on the top of the first one, the tube is inverted, there is air on top of it. And because of that, pressure that will be acting at that point will be H atmospheric pressure minus what is reading, 73.5, which keeping 1.5. Then the correct barometric height of the container when the volume is 6 and reads 74. So that means the height of the container at that point, which I don't know, minus the 74, which is the height in which it is reading. So I am saying pressure is a dependent of height. I'm using my formula to relate. That is why you need to understand how to solve questions. That is why we have illustration. So directly, you can just say we have the first pressure, we have the second pressure, but here we are giving in terms of volumes. So directly, we can just conclude and say, fine. From Boyle's law, to solve this, because the question asks for the volume, the height. From Boyle's law, from early classes and from your chemistry class, from Boyle's law, we can say P1, V1 is equals to P2, V2. Why am I doing that? Because I know pressure is related to volume according to Boyle's. So directly, I can just put values and get it. The first pressure I have here is 1.5. I'm multiplying that with the first volume given in the question was 8. You can see that multiplied by 8 is equals to the second pressure is now H minus 74. I'm also multiplying that by the V2 here. The V2 here is 6. So directly I can say here, this is 1.5 times 8 is 12, fine, is equals to, here we can just do, this is 74, okay, fine. H minus 74 into bracket 6. So finishing this, we can say, therefore, divide both sides by 6, everybody know, 12 by 6 is going to give you 2, is equals to H minus 74. So doing this directly, you can say H is equals to 76. As if you move this to the LHS, you have 2 plus 74, and that is 76. We are working in centimeter, and that is the answer to the question. So, guys, this is the way you solve questions like this. Be careful about understanding the position of the tube, the atmospheric pressure, that is the initial one, when there is no space. When I told you practice makes perfect. Practice make perfect. So keep that at the back of your mind. The last for today is question 4, which is water flows along a horizontal pipe of cross-sectional area 40 centimeters square, which has a constriction of cross-sectional area 10 centimeters square. Which has a constriction, okay, of cross-sectional area 10 centimeters square at one point. If the speed of water at the constriction is 4 meters per second, and the pressure is 9.0 times 10 raised to the power 4 Pascal, then the pressure in the wider section is dash. We're given the constant, this is our density of water is 1,000 kilogram per meter cube. And this question was extracted from JUPEB, question 26, year 2014. Oh. But according, like what I said before, I am not always the one that prepared the slide. It's always prepared by the student. I'm just there to just give solutions to them after I've explained concept. But looking at this question, because of what I have, we can say solution to this directly. To this illustration 4, which is the last illustration for this video 1 tonight, we can directly say the first area 1 given here was 40 centimeter square, and the second area is area 2 is 10 centimeters square. So because it was constricted, that means it was narrowed. So this will bring us to another thing which I have not, which I have not explained. So, and that is why I'm not going to talk much about this, because this will give me what we call Bernoulli Principle. I can give you as an activity to try, and that will come in the third part of the video. That is talking about hydrodynamics. I will talk about Benelli Principle, the pitot static tube. I will also consider Stokes' law and terminal velocity, as well as all what is required in your syllabus. I'll talk about the Poiseuille equation, and we'll talk about rate of flow, Reynolds numbers, and as many things you want to learn with respect to your syllabus. I will not take more than what your syllabus is required, and we only concentrate and pick questions from them. So from what I'm trying to say here, we can only solve this if we have gathered the knowledge of Bernoulli's principle. But for now, we are yet to gather the knowledge. I think maybe my students think the question will actually fall to what we have studied, but no. But if you want to try it, it's a simple way. What you need to know is that you first of all get the speed of the second one from A1 V1 is equals to A2 V2. I know some of you are ready for the exam and you have an idea about this. You get the cross-sectional area at the speed of the second one. And having done that, you now come to the Benelli Principle, which says the first one is P1 plus the pressure in the fluid from energy conservation. Don't worry, I will explain all this. Then you have plus half rho V squared is equals to the second one, P2 plus rho Hg. I love writing rho Hg, but you write it as H rho G plus half, the second one is density of the liquid and V2 squared. Let's take this one as PV1 squared. So here we can say this will get cancelled out. So directly you can now solve as this and this. So you are looking for P2, you bring this one to the right hand side, substitute the value, and you have the answer. So you have gotten your V2 from what the formula I gave to you. You can try it, but for now, I will take that as what you have not learned. So in the next video or in future video, when we get there, you are still going to learn on how to what derive this, because derivation sometimes is important. So see you guys soon. This is where we stop. Don't forget to subscribe, share, and like the video for more. And you can also follow us on Telegram and any platform of social media. You search for Mosey Academy. We are always there. Thank you and see you soon. Bye.